So, folks, colleagues, thanks for being here today. Thanks, Ignacio, for also presenting today. As you know, we are organizing seminars for those junior assistant professors that are joining the department with a dual objective. First, for them to present what they're doing, and for you, us, to also get to know what they have done and what they want to do. And eventually, the objective is to exploit synergies, find collaborations, opportunities, foster discussions, and this scientific debate that must be within the department. All right? So thank you very much, Ignacio, and the people for being here. Ignacio has been studying abroad in the bachelor in US, in Maryland, and Illinois. You don't say what is your discipline, but I guess it's aerospace. Aerospace engineering. Then he did a PhD in University of Cambridge. He has been always focused on guys, I have arriving late is okay, but please stay silent. Thank you. I lost the thread. So he did a PhD in University of Cambridge, always dealing with aerodynamics, fluid mechanics, and 2 years ago he joined the Emirates New Zealand team from the America's Cup, so sailing, and he has been working there, which I guess was quite fascinating, like the Formula One of the sailing. And then he decided to move here to start an academic career with us. So, floor is yours, Ignacio. Thanks for being here again, and all the best.
Cool. Thank you for the introduction. So today I'm going to talk about my main area of expertise, unsteady wing aerodynamics. I'm going to talk about the topic in general and also what has been my path, some of the things I've done. And I'm going to try to tell a story, and let's see if it works. So the clicker needs to work first. Stories. Yeah. So we all know about steady wing aerodynamics. We have an airplane that is cruising. The dominant flow features don't change with time. But then what would happen if, for example, the clicker doesn't work very well, but if the wing starts moving like that was my attempt for an animation of a flapping wing. So this doesn't usually happen on airplanes, maybe some fighter planes, but it happens all the time in the flight of insects. And if we look at how, for example, bee flies, we get that they are flapping their wings very rapidly. And bees are very good at two things. One is to fly with a very small wings and very large and relatively heavy bodies. And they are also very good at flying at low Reynolds number. And these two things are things that humans, we haven't been able to replicate very well. We haven't been able to design a vehicle that does this. And part of this is because we don't fully understand the unsteady aerodynamic behavior that governs this type of flight. Another example is that of helicopter rotor blades. So this is a pretty general example. And we know that the blades of the helicopter are rotating all the time. But as you know, they are also pitching. This is a video from the middle of a helicopter blade looking outwards, and hopefully you don't get dizzy when I play it. I'm going to use maybe this. But now we can see very clearly that the blade is rotating, but it's also pitching up and down all the time. So a bit similar to the flapping of a bee, except for the rotating motion. And this is to maintain the same lift, obviously, in the advancing and retreating part of the blade. And the last example I'm going to show is related to sailboats, because I had to add an example of sailboats. So sailboats have two very nice big vertical wings, also known as sails, and you can see them here. And these are very high performance boats. So when the boat is going a straight line, it's governed by steady aerodynamics, like the airplane. But when it turns, I will show you, and you can especially focus maybe on the front sail. As it turns, the front sail is going to move from one side to the other side of the boat fairly rapidly. And this is going to create a lot of unsteady aerodynamic effects. It's a bit like changing the angle of attack of a wing from positive to negative values. So this is one of the first ingredients that we need for unsteady aerodynamics is a wing that is moving rapidly. And to define rapidly, we don't only need to account for the time that it takes to do some motion, but also we account for the convective time. And we use, as many of you know, the reduced frequency, which is the ratio of the convective time and the time that the motion of the wing takes. A way of looking at the reduced frequency is related to how much one particle of the flow would convect downstream every time the wing makes a motion. So the wing pitches up and down, and this is the distance the particle travels, and the reduced frequency is the inverse of this. So we can take the reduced frequency and draw like a plot, one-dimensional plot, where we have that the wing aerodynamic cases with a reduced frequency of 0 are basically steady. And as we increase this number, the unsteady effects become more predominant. And we can plot here the examples that I showed. So cruising airplane is basically steady. The case of a helicopter blade is fairly unsteady. And this is an approximate of the order of magnitude of what it usually looks. The sailboat changing direction actually came up as more unsteady, and this is because the chord is a lot bigger, so the convective times are a lot bigger, so the unsteady effects are slightly bigger. And the big winner was the bee. Even though it has a very small wing chord, it's flapping its wings so fast that the unsteady effects are very important. And to study all of these cases, the unsteady cases, these are very complicated to understand all the aerodynamics around them. So many people, what they do is they do experiments or computations on a specific case. And then once they get the results from those, they try to understand what's happening there. And this is what I did for my master's. So I did experiments on a wind tunnel of wing that you can see here that was basically pitching up and down. So similar to the helicopter blade without the rotating, just the pitching up and down. And I was taking force measurements as well as PIV measurements, so to recreate the flow field around the wing. And I took PIV measurements at different span-wise locations, so I could recreate the flow field of the entire wing, approximately. And this is how it looked. So we have the wing in gray, and we have the different regions of the flow field with different colors. And what I was looking at is what happens with the three-dimensional effects as the wing is pitching. So the wing is pitching up and down, is pitching to fairly high angles of attack, so we have some separation. And here you can see a blue region that corresponds to the part of the flow that is separated. Then we have like a red region close to the wingtips where we have a leading edge vortex that is being shed. And then the yellow region is like a more developed, if you wish, leading edge vortex. So what we can see is, because we have three-dimensional effects, we have the effect of the tip vortices, the unsteady evolution along the span-wise is not homogeneous, it's heterogeneous. And different things happen at different span-wise locations at different times, as we can see here. So basically, in the middle of the wing, we have a more evolved flow than at the tips. And then we can measure the forces on this pitching wing. We can plot here the lift versus the angle of attack through the pitch motion. So in blue, we have the finite aspect ratio wing of aspect ratio 4, so pretty short. And in gray, we have a two-dimensional airfoil, infinite airfoil. And we can see that because in the finite wing, the unsteady separation effects occur at different times, at different span-wise locations, it's a smoother curve that it hasn't fully stalled even at 22 degrees, while the two-dimensional airfoil with the same airfoil section has stalls around 18 degrees or so earlier. So this is what I did for my master's, and this introduces what I think is the second key ingredient in unsteady aerodynamics, which is the shedding of vortices. So we have a wing that keeps moving, and we have a lot of vortices that are shed from the wing different times, and again, they change with time. So with these two things in mind, we can look, for example, at the flight of a dragonfly. So here we have a dragonfly on the left and some simulations on the right. And we can see all of those blue blobs of vorticity, which are vortices that are being shed from the wings of the dragonfly. So you can see very nice flow, also very complicated, a lot of things going on, changes with time and all of that. So after my master's then, when I started doing my PhD, I was under the supervision of a professor that was a pretty big fan of, instead of looking at a very complex problem and not being able to go very in depth or understand it very well, try to simplify things like the geometry or the motion of the problem, so you can have a simpler problem that you can understand more fundamentally. So instead of looking, for example, at this insect, we could look at only one wing instead of all the wings. We can get rid of the three-dimensional effects. We could look at one 2D plane on the wing, so we have just an airfoil. And instead of this very complicated motion, we could have just a wing that is accelerating from rest. So simulating, for example, the takeoff of an airplane, where the wing is at rest and is going to accelerate forward. And this case has been studied for very long, as you can see by this video. And this is what we have here, a two-dimensional wing that is at rest. And if I play it, it's going to accelerate forward and start moving forward at a constant velocity. So again, this is a well-known flow that has some important characteristics. One is this shedding of a single starting vortex, trailing edge vortex, as well as changing in the flow velocity around the wing. And this flow velocity, we can relate it to circulation, like we do frequently in wing theory. We can also relate it to a distribution of vorticity along the wing, which is basically the wing boundary layer. This vorticity is present in the wing boundary layer. But basically, all of these are related, the velocity field, the vorticity field, and the circulation. And in steady aerodynamics, we could calculate the force on the wing due to a flow by calculating the change in momentum of the flow that is in front of the wing and the change in flow, the change in flow of momentum of the flow in front of the wing and downstream of the wing. But what happens in unsteady aerodynamics is that many times we have these vortices that are very close to the wing, and it's difficult to understand if these vortices affect or produce a force on the wing or not. So what we have to do in unsteady aerodynamics is to take into account the entire flow field, not just the flow upstream and downstream of the wing, the entire flow field and all the vorticity in the flow field. And we can use an equation, momentum balance equation, which looks like this one, which is basically force is equal mass times change in momentum of the flow. But we are just expressing this in terms of vorticity instead of velocity. And this is frequently known as the impulse method to calculate the force of this flow. And this is the change in momentum in the vertical direction, in the y direction. So this would be the lift force on the wing from the vorticity field. To understand this a bit better, we could simplify the problem again. And let's say that instead of a vorticity distribution along the wing, we just have a single vortex. So we have a single vortex for the trailing edge and for the wing vorticity. And then our force equation for the impulse method simplifies to this. We don't have an integral anymore. And we can see that there are two things that can happen in the vorticity field that produce a force. The first term says that two vortices, a vortex pair that are moving away from each other, are producing a force. So something like this. If one of the vortices is moving from the other, it is producing a force. And the other term says that two vortices that are at constant distance from each other, if they increase in strength, they are also producing a force. Cool. So what happens in steady aerodynamics, again, we have a starting vortex that is very far away from the wing. And basically, we only have this first term, and this is the velocity of the wing, or the free stream velocity. In unsteady aerodynamics, we have now a wing that just started moving forward. So it just started shedding some vorticity. So maybe at some time, the flow looks like this. This is the small trailing edge vortex, and this is the vorticity distribution along the wing. And at some later time, maybe the vorticity looks like this, where we have a bigger trailing edge vortex, and the vorticity around the wing is different. So the vorticity field is changing, the force that this flow is producing on the wing is changing, and we can calculate the lift on this wing during the starting maneuver, and this has been studied very extensively. And the lift response looks something like this, where at the very beginning of the motion, we have about half of the steady lift, and then the lift slowly convex to the steady state value if nothing else happens, and the wing just moves at constant velocity. All of these forces, so the forces, something that we did a lot during my PhD, is that we have some force contribution that comes from the vortices that are shed from the wing, and these are the circulatory forces, and this is what I just mentioned with the starting vortex, and this is to differentiate it with another important unsteady force of the flow, which is the non-circulatory force, or the added mass force. And to understand this added mass force, we could look at a different simple example, which is a flat plate that is traveling perpendicular to its chord. So it's basically at 90 degrees. This is a flat plate traveling at 90 degrees. It has been moving for a bit, so it has some vortices, or positive and negative circulation on both sides. And these vortices are producing a force on the wing, but in addition, this wing is also moving some flow. So it's moving flow around it. So it's basically pushing flow out of the way in front of it, and then pulling flow on the back. We can look at it easier probably if we go back in time a bit and we look at the very beginning of the motion. So the flat plate has just started moving forward, so it hasn't had time to shed any vortex, so we don't have any circulatory force. But because it is moving forward, there is some vorticity in the flow. This vorticity is in the boundary layer of the wing. And actually, if we represent the streamlines in the reference frame where the wing is stationary, the streamlines would look like this. So you can see how the flow turns around the wing, and it creates some vorticity. And to calculate this force, we could calculate the volume of flow that we are being displaced by the wing and multiply by the acceleration of the wing. But to be consistent with what we have been doing, which is calculating forces based on the vorticity, we could calculate this force also with the vorticity field that we have here. So we have, again, to simplify it, we have one vortex at top and one in the bottom, but this is a distribution of vorticity. And what happens is that when the wing is accelerating forward, these two vortices are increasing in strength. And because, there are some y distance from each other, increasing in strength, we are going to have a drag force, horizontal force in this case. If the wing is moving at constant velocity in this direction, this vorticity is not going to change in strength, and while the vorticity is going to be there, is not going to produce any force. So this non-circulatory added mass force is associated with wing acceleration of the wings. And actually a lot of this work was done by Corkery, which was another student in the same group I was doing the PhD. and he measured the vorticity, experimental vorticity of this wing, and he showed that he could get a very similar result for the theoretical vorticity that comes again from this flow. So this is what was actually happening in the experiments. And now I'm going to introduce something that I hadn't mentioned yet, which maybe is the third ingredient for unsteady aerodynamics. And this is that in some cases, instead of having a wing that is moving, what we can have is flow that is moving around the wing, and the wing is not moving itself. And this is the typical wing-gust encounter case, which is also very largely studied in unsteady aerodynamics. We can represent it again. We could have a vortex in the flow that hasn't come from our wing itself, but it's an external vortex, and this is one example of a gust that may be convecting and going around our wing. And for the wing-gust encounter cases, we can define a gust ratio, which is the speed of the gust with respect to the speed of our wing. So a big airliner that is traveling very fast usually doesn't encounter gust with very high gust ratios because there is a maximum velocity in the atmosphere that we can also usually encounter. But my PhD was especially focused on high gust ratios. So when can we encounter high gas ratios in the vehicles that we design? This is usually when we are looking at small vehicles that travel slowly. So this is one example. Here we have, again, a small quadcopter that is taking off from the roof of a building on a windy day, and I can play it. So it takes off from the roof of a building on a windy day, and it wants to fly forward to complete some type of mission. But as soon as it reaches the edge of the building, it encounters strong changes in the flow, and it loses control and it crashes. So not very elegant flight. On the meantime, in nature, we have things like these birds, which are called kestrels, and they try to keep their eyes very stationary to have a good eyesight. So they also want to keep their head very stationary so they can make use of their very good eyesight. And they take advantage of external wind and external gas that comes to them. And if you can see how they fly, you can see how elegantly they fly on a windy day with different gas. They keep their head very, very stationary. And one of the things that they do to be able to fly so precisely is that they do rapid wing motions to mitigate, to cancel out any gas that is coming externally. So this is pretty much what I tried to do for my PhD, try to understand this a bit better. Again, I did some experiments on a water tank. So this is a water tank, this is our wing, this is vertical, and we are towing the wing forward, so the water is stationary. And this permits us to create to put inside of our water tank what is essentially an open section water tunnel. So it creates a cross flow there. So the wing is moving forward at constant velocity, and eventually it encounters this external flow velocity. And again, I took force measurements as well as flow velocity measurements. So these are the results from the flow velocity measurements in one two-dimensional plane. This is our wing, which is just a flat plate. It's traveling forward, and it encounters this upwards gust, changing external flow. Oops. And if we look at what happens as the wing enters the gust, as you could imagine, we have a very strong leading edge vortex that forms, and a lot of trailing edge vorticity also that is shed. And we can play this next to the lift on the wing, so the performance. And we can see that as soon as the wing enters, we have a very large increase in lift to a CL of almost 6, as we are shedding this vortex and we are experiencing this external vorticity. And this is kind of the very big force that you could imagine the drone to have encountered and then lost control because it wasn't expecting it, basically. to mitigate this large lift peak with a wing motion. So I was and a 1 degree pitch motion. So we have this is our force that we want to mitigate, and we want to move to pitch the wing in a way that we are able to achieve constant lift through the entire wing gust encounter. And to be able to do this, what I assume is that I can measure the flow in front of the wing. So I can measure the external flow that is going to be affecting the wing a few milliseconds later. And then I need a way to, using that measurement, calculate what is the wing motion that would mitigate this external flow completely. So to be able to do this very quickly inside on board of the airplane, I started studying about low order models of aerodynamics, physics-based low order models, which basically they are pretty popular. They get rid of the things that maybe we assume are not completely necessary to try to keep what is most essential and then be able to calculate things very fast. So what they get rid of is, first of all, the leading edge vortex, that in my opinion is the biggest problem with this, especially for my case. We are assuming that there is no leading edge vortex, all the vorticity is set from the trailing edge. We also get rid of viscosity or rotationality, so we assume the flow is irrotational, which is the second biggest problem in my opinion. We have, however, these point vortices to represent the flow. So they have a singularity in the center, and they can represent an irrotational flow. Same for the boundary layer of the wing. And then we have also that all the vorticity is only convected by the free stream. So it's very organized like this. We got rid of a bunch of physics, but then with this, and we get some very big advantages. Like the main one that we were looking for is that we are able to calculate the forces due to the flow in fractions of a millisecond. So we wouldn't be able to obviously use computation, CFD, or experiments to do this. In certain cases, the results from these models are fairly accurate, especially when you don't have a leading edge vortex and the angle of attack of your wing is small. And they can help sometimes also to understand what is the physics, some of the physical concepts of this type of unsteady problems. So with these models, and doing a bunch of research, I came up with this equation, which, again, uses a lot of work from previous studies. But this equation, is not as complicated as maybe it seems at first. It has a Wagner function and a Kessner function that I will explain in a second. It has a term that calculates the force due to the circulatory force due to the wing motion. So it's important to include this component of the force. We have another term down here that calculates the non-circulatory force of the wing motion. And then we have another term here which calculates the circulatory and non-circulatory forces of the wing gust encounter. This term includes high angles of attack effects. And then I included this additional term for the wing gust encounter that also includes high angles of attack effects because, like I said, we are interested in high gas ratios. So the wing motion is going to have to be pretty drastic. It's going to have to include pretty high angles of attack. And then we get this one-line equation that relates what we want, which is the lift on the wing that we want to mitigate, the gust velocity, which is what we are measuring, and the wing angle of attack, which is what we want to solve for, the wing motion that we want to solve for. So then using this equation and knowing the things in blue and everything else except the angle of attack, I could calculate what is the pitch profile of the wing that would mitigate the wing gust encounter. And this is one example of the results I got. So now we have the wing that is going to enter the gust, and it starts pitching down very fast as soon as it enters. there is a leading edge vortex, but the leading edge vortex is much, much smaller, as you could see, than what we had before. And all much, much smaller than what we had before. And also you can see that our objective of maintaining lift close to 0 was achieved fairly well with only a 1 degree motion of pitch, and using, again, a lower order model that neglects many things. And I think that one of the main reasons why the lower order model was able to do fairly well is the fact that in this case, the leading edge vortex is a lot smaller. So we can use this model to mitigate a wind gust encounter, because the mitigating result has a small leading edge vortex. If we were trying to model something that the final result has a large leading edge vortex, we wouldn't be able to mitigate it. We wouldn't be able to use this type of lower order models. So these are some examples of a lot of the work that was used to come up with these lower order models and to study unsteady wing theory in general. But before coming here, I noticed that a lot of the work I had done and I have looked at was related to the lift in the unsteady wing aerodynamics, the lift. So when I came here, I had some experimental data for the drag also. So I was interested to see, well, what can I do with the drag data? And I started looking at the literature, what has been done with the unsteady drag for wing theory. And well, this is just to show you that I don't mind too much if we get results for a wind gust encounter, which is at the top, which is a wind encounter in some upwards gust, or a wing motion, because there is a way to go from one to the other. So both results would be okay for me. But when I was looking at drag research, I found very, very little information. So if any of you know more about unsteady drag that this work, let me know. But basically, I couldn't find any work related to the drag during wind gust encounters for high gas ratios and wing theory. And I could just find very small number of studies on wing theory for the drag of a moving starting wing. So with this in mind, one of the reasons I thought that maybe there wasn't a lot of lower order models to represent drag is that one of our assumptions say that our wake is in the horizontal plane. And usually the equations we use to calculate the force, again, we need to have some change to get the drag force. We need to have some y coordinate of the vorticity. If all of it is 0, it may seem that this equation is 0. So what I did was to move the vorticity to do a change of coordinate system. So the vorticity for my lower order model looks more like this. So it includes the fact that the vorticity on the boundary layer has an angle of attack. And then following the procedure by other people for lower order models, I got this result, which I don't know if it's out there, but it's basically that the drag is related to the lift and some amount of circulation. At the same time, I was looking at the literature again, and one of the papers that I found was by Fernández Feria. And Fernández Feria did something very similar to what I was showing here, but instead of doing it for a starting flat plate, he did it for a pitching plate. So what he was doing, or what he has done, is to assume some shape for the vorticity of the wake. And once you assume that shape, you can use these lower order models to calculate the drag. And he showed in his paper that his solution was better. Sorry, I should have mentioned that these guys here, they did provide a solution for the drag of a moving plate, of a moving wing. But Fernández Feria showed that his solution was mostly closer to some computations and some experiments, where he again was assuming the wake of the vorticity shed. And so he concluded basically that maybe the work that was done many years ago, they were missing something. And as some of you probably saw, Gordillo, which is another Spanish professor, so a lot of Spanish professors looking at this, he came to this university to give a seminar a couple months ago, and he was talking exactly about this unsteady drag force. But Gordillo conclusion, so Gordillo was able to calculate the drag using the impulse method for a horizontal wake, using a more fundamental equation. And when you do that, you get the same result as the original classical work from many years ago, which makes sense. And he just concluded basically that Fernández Feria got a result closer to some experiments and some computations because he had assumed a more realistic shape of the wake. So this is something that, well, has started to interest me, and is one of the things I'm looking at. But just to finish and to show that even though this topic has been around for over 100 years, the topic of unsteady wing aerodynamics, everyone pretty much agrees that for low order models, the lift of accelerating wing is like this, 2 pi alpha and the Wagner function. But if you go into the literature and try to find an equation for the unsteady drag, you have one group of people, again, which seems pretty strong group of people, that say that the unsteady drag of an impulsively starting wing should be represented as this. Then there is some work that shows that it can be represented as this. So as you can see, it's fairly similar, but the second term is different. And maybe, again, this we are assuming the shape of the wake, which is less consistent mathematically, but we'll see if it has some advantage. And interestingly, also when I was looking at the literature, I found a bunch of studies that when they come to the drag force, they just say 0, which in a way it makes sense because the angle of attack is a square term. So it's alpha squared instead of just alpha. So maybe, yeah, if you say that you're assuming small angles of attack, you just say 0. But I found quite a lot of inconsistencies basically in the literature. And this is something I'm looking at in addition to applying these concepts of unsteady aerodynamics to other applications like wind turbines or cavity flows. And with that, I'm going to finish.
All right. Hello. Yes, it's working. Thank you, Ignacio, for your presentation. Questions in the audience? Don't be shy. No question. You're going to let me the responsibility.
Yeah.
Or if you want to go. No.
Ignacio, thanks a lot for this nice presentation. One question that comes to my mind when I think about what you just finished to explain about drag, and so the low order drag models, and and when you compare these results with experiments, you said you have experimental data on drag, is how, so all the low order models, for what I've understood that you've showed, you make the assumption of inviscid flow, so you don't consider viscosity. So how, when you look at the experimental data, you do have viscosity
yes,
there,
yes,
of course.
So
my question is, how, let's say, how can you see, when you compare, let's say, your low order model with your experimental results, how can you pinpoint how much of the, let's say, difference that you will get is because of the viscosity? If that is clear.
Okay, yeah, that's a good question. And kind of the next step I have to do is to compare these low order model results, like the two different options, to the GAST data I have. Obviously, with the lower order models, we are neglecting viscosity, so we don't have any viscous drag. So Fernandez Feria, when he did his comparison of the lower order models with the experimental results, he just he subtracted the viscous drag effect from the experimental results, and he compared only the pressure drag, essentially, the unsteady pressure drag. Yeah, it's a good question of exactly how to make sure that we are, well, in my case, for example, of a wing that is traveling at constant speed, the viscous drag before entering the gust is probably going to be a good representation of the viscous drag when it's inside of the gust, and the remaining is going to be the unsteady pressure drag. But it's a good question to take that into account.
No, because especially when you have the impulsive starting wing, then essentially you kind of have a varying Reynolds number, and so like the importance of one or the other term in terms of drag is constantly changing.
Yes.
So I mean, it's an interesting problem to look at. Thanks.
Yes.
Thank you. No questions, then I go, if I may. Okay, if you go to all your initial, your motivation of the topic, all the different unsteady aerodynamics problems that you've been tackling, maybe you can go there to see those. The timeline that you have, right? That would be, yes, here. We were seeing different examples, and that was nice, and you were kind of raising a lot of expectations on how we could understand this in real life, which is a very interesting problem, especially when it comes to nature and mimicking nature, which should be the ambition of humans. But then all the rest of your talk has been devoted to quite simple models, which makes sense. It's models that we simplify things to understand what's happening there. Right? But I guess, I don't know if you have the ambition in the maybe medium term or long term to really tackle any of these problems more realistically, right? And I can tell you that here in the department, well, right? There has been computational fluid dynamics applied to flapping wing, and I don't know how far you are from, or how could you leverage your canonical models to really start to ambition to tackle this type of problems, eventually understanding the dynamics, and eventually controlling the flow, maybe going into reinforcement learning, which seems to be the way nature learns, kids, maybe animals, because how to control the flapping according to what you're seeing, this cross-slope behavior. So I don't know, what are your thoughts about a bit more long-term vision on what your research could evolve towards?
Yes, well, one of the possible paths is, like you said, we have the reinforcing learning models. There are some people in the department here who do that type of work for fluid dynamics, and they have some advantages and some disadvantages, and maybe adding some physics to them. Again, in both cases, the objective of those models and physics-based lower order models is to get results very quickly. But something that we could try to do is to combine the reinforcement learning models with some physics-based models to make them stronger, and at the same time keeping their fast computation. Then all the part on the differentiation between the circulatory and non-circulatory force, that is, those are mostly experimental results that exist, and you can, so the momentum balance equation of the vorticity field, you can do it in a real flow experimental data or DNS to try to understand what's happening better. And you can do it in the lower order model also, but it's something that applies to lower order models as well as all of this. And part of the path that I hope to take is to to start to add some complexity to some of the problems, like like if you want to study the aspect ratio, the three-dimensional effects are very important because it has a very low aspect ratio wing.
I think that mixing or merging this physics-based information into machine learning approaches is trendy today, and I think it's a good way to go. Yeah. Other, yes. Last question. Don't be shy. No. Okay, Mario.
Well, thank you, Ignacio, for the talk. What you presented got me thinking about the gust and the wing that goes horizontally into it. And I was thinking how this is handled on actual airplanes, if it's handled at all. Would it be possible to perform a similar study where instead of tilting the pitch angle of the whole wing, you have a control surface at the end, say an aileron or something, which you can use to cancel out the upwards force caused by the gust? Would you think that would be meaningful and perhaps something that could be applied in airplanes? Maybe it's already applied. I don't know.
Yeah,
I don't know what is the state of the art.
Airplanes are doing some of it.
Okay.
One big difference is that, again, airplanes have they encounter low gas ratio gust, so the velocity of the gust compared to the velocity of the wing is pretty small, so some of the physics changes, but like so from my previous group where I did my PhD, the next student coming after me, he started doing exactly that. Okay. So we already had these results, and now he was looking at having a wing with a control surface.
Well, the gusts are small, but they are not that small. I mean, you can feel them when you fly. So
yeah. But I think this one you will feel a lot more.
Okay, thank you.
Yeah.
Okay, thank you. So I think it's time to close. Thank you, Ignacio. I guess, well, you know where he lives or his office.
My office, yeah.
Office number 16, I guess.
The same as Maria, 20.
Just in front of Oscar's or next to mine. So if you want to knock his door, get to talk, discuss, find potential collaborations, I think, well, you know more or less what he has been doing and some of his ideas. I was asking a bit more towards the future to also find some potential, I don't know, interaction with machine learning people or control people or drones, I don't know, whatever. And he has a very nice sailing Lego, how do you call it? Model. Yeah. If you want to go and check. Okay. So thank you very much, Ignacio, and thanks you for coming as well. Bye-bye.